Hi. The second application of the extended implicit function rule and theorem that we're going to discuss is going to be ISLM model with general functions. And look, I know that at the beginning, using these general functions and implicit function rule might be a little bit problematic. But I hope in this case you will see the benefits, because this is going to be the first time when we were calculating before we had so much to do. Now it's going to turn out that it's going to be very simple, and we can easily find everything that we were striving to do before. Okay, and look, let's start with this simple introduction. And of course, let's start with IS curve. Actually, everything we did all the groundwork for IS curve a couple of videos ago when we were discussing national income model. And look, generally, IS curve is responsible for equilibrium in markets for goods and services, right? So we use, of course, the same equations that we were using when we were dealing with a national income model with general functions. So, what do we assume? First, we've got equilibrium condition. Income equals aggregated expenditures. Aggregated expenditures are the sum of consumption, investment, and government spending. Government spending is given exogenously. Investment is a function of an interest rate. All we know about it is that the higher the interest rate, the lower the investment, right? We get it from this derivative. And consumption is a function of disposable income. But of course, disposable income is a function of income minus taxation, and taxation is also a function of income, right? Derivative dc dy, right? So by how much consumption increases when GDP increases by $1, let's just say is our NPC, and here the first derivative is a tax rate. So I just wanted to remind you that when we calculate this derivative of consumption with respect to income, we are using the chain rule, right? We put dc over here and dy over here. And what? Look, if income changes, that impacts disposable income, and then in turn, disposable income impacts consumption. So what I'm going to put here is dy dy. We know that this is true, and we can easily calculate it, right? First, here we've got marginal propensity to consume, C prime, and over here, derivative of disposable income with respect to income. So first we have 1, and minus T prime, right? T prime is of course dt dy. So, this is the most important derivative that we need to use when we want to use this model. Okay, and look, so basically, all we've got to do to use this model in a general form is to condense those equations into 4 equations into 1, and we just do it by simply substituting the first equation, second equation to the first one. So we've got y equals c yd plus I plus g0. And look, this equation that you see over here is our IS equation. So now let's find slope of IS. Look, again, we will be drawing our ISLM model just like before in income interest rate space. Now, we just don't know how the functions look like. But we can find slope in the same way. So, by calculating differential with respect to income and interest rate. So, let's do it. We've got that. dy is equal to derivative of this with respect to income times change in income. So, c prime 1 minus t prime dy, right? Then plus I prime times di, right? Okay, let's put all the expressions with dy's together, and we get then that this is 1 minus c prime, 1 minus t prime dy equals I prime times di. Now, let's reverse the sides, and let's reverse the sides of the equation. Okay, let's do it slowly. And what do we do next? We divide both sides by dy and I prime. And we get the derivative di dy is equal to 1 minus c prime 1 minus t prime over I prime. Now, we know that this is somewhere between 0 and 1, right? Expression downstairs is negative, so we can be sure that the slope of IS is negative. And look, in this case, it doesn't need to be a straight line. We just know that IS is some downward sloping function in income interest rate space. Okay, so now that we've discussed IS, let's move to LM. With LM, again, it is way easier because there's less components. So here we will have that demand, money demand, is a function of income and interest rate. L stands for liquidity, demand for liquidity. And we are assuming that Ly, which is defined as derivative of L with respect, so money demand with respect to income, is positive. So the higher the income, the higher the demand for money. And Li is derivative of L with respect to interest rate is negative, which means that the higher the interest rate, the less money we want to keep in our pockets, the more we want to keep in the bank. Now, money supply is still so M0, and which is given exogenously, and equilibrium condition is money demand equals money supply, or in this case, Ly. I equals to M0. And again, just like with case of IS, we would like to find the slope of LM. So, we take this equation and we calculate its differential with respect to income and interest rate. So we get that this is Ly dy plus Li di equal to 0. If I move this expression to the other hand side, I'm getting that this is Li di equals negative Li dy. And dividing both sides by dy and Li, I'm getting the derivative di dy is equal to negative Ly I. Now look, we already said that this is positive by assumption, this is negative by assumption, minus and minus gives us plus, so we know that this derivative is positive, which means that the slope of LM is positive. Again, we don't need to assume that the function is linear, must have some general upward sloping shape. Okay, so now that we finished with the basics, we know how IS comes about, how LM comes about. Let's get into actually finding comparative static derivatives of this model. Okay, and look, we start just like we started before. So, first, we need to set up function 1 that is going to be a function of income and interest rate as endogenous variables and government spending and money supply as our only two exogenous variables. Now look, our equilibrium condition, generally our IS equation has the following form. So, we want it to be in the form that something is equal to 0, right? So all we gotta do is to subtract this side from this side. You get that this is y minus cy d plus minus I minus g 0. And this is going to be our first function, and we know that this is equal to 0 from this function. Then we create the second function with the same endogenous and exogenous variables, but this one is associated with LM. So look, we use the very same trick. So I subtract m0 from both sides, so this is equal to 0, and I'm getting Ly I minus m0 equals to 0. What do I need to do first here? Of course, first thing is to calculate a Jacobian. Okay, let's do it slow first. Remember, here we got first function, here we've got second function. Here we differentiate with respect to first endogenous variable, here we differentiate with respect to second endogenous variable. Okay, so if I differentiate this with respect to y, I'm going to get 1 minus c prime 1 minus t prime. Now, if I'm differentiating this equation with respect to interest rate, I'm getting negative I prime. Now I'm doing this for the second equation. If I'm differentiating this equation with respect to y, I'm getting Ly. And with respect to I, I'm getting Li. So, now I just need to calculate it, and it turns out that this is equal to 1 minus c prime, 1 minus t prime, Li plus I prime times Li. Now, what do we know about these expressions? Well, we definitely know that this is between 0 and 1. We definitely know that this one is negative. We know that this one is negative, and we know that this one is positive. Alright? So those two together give us a negative expression. And to this negative expression we add another negative expression. So we can be sure that the Jacobian here is always negative. What does it mean for us? Look, here, let's start with graphical interpretation. Graphically, it means that there exists a point where IS and LM intercept with one another. But for us, it also means that these two functions are implying different functions, two different functions that are actually of interest to us. Those two functions are, of course, the functions of endogenous variables expressed as functions of exogenous variables. So in our case, this is y as a function of government spending and money supply, and interest rate equilibrium as a function of government spending and money supply. Okay, so knowing this, that because Jacobian is different than 0, is always negative, we know that now those functions imply those, they have the status of identities around equilibrium, so I can rewrite this equation in the form of and the second equation, of course, in a similar way. Okay. So, what do we do now? Now, we're going to calculate total differential of both of these equations. So, I'm getting that this is dy with asterisks minus c prime 1 minus t prime dy with asterisk minus I prime d I prime minus dg0 equals to 0. And then we've got ly dy, let's call it just dy, plus li di minus m dm0. Okay, what do we do in the next step? I'm going to put all exogenous variables on the left-hand side and the endogenous variables on the right-hand side, and I'm going to collect those terms here. So I'm going to get that this is 1 minus c prime, 1 minus t prime, dy minus I prime di equals to dg0. And over here I've got ly dy minus li times di equals to dm0. And this is something that we can actually put into a matrix notation. Okay, so I'm building a matrix of coefficient first. So this is going to be 1 minus c prime, 1 minus t prime, ly minus I prime, li d I equals to dg0 dm0. Okay, and look, this is a system of simultaneous equations that we can work with really, in a really pleasant way. What do I mean by this pleasant way? Okay, look, we don't need to solve it. We don't need to know what is I with asterisk, y with asterisk, and I with asterisk, in the sense that we don't need to know how does it exactly look like. We're going to do our reasoning based on derivatives. So the only thing that we should take into account is that we know that Jacobian is different than 0, and Jacobian is equal to 1 minus c prime, 1 minus t prime, li plus I prime ly, and we know it's lower than 0. Okay, let's just say now that I want to know what are the effects of fiscal expansion. Okay, look, we are using the same tricks that we used previously. What do I mean by that? Look, if I want to assess what is the effect of fiscal expansion? What should I do first? Well, I should assume that G0 is different than 0. Right? Government increases the level of spending. However, at the same time, I must assume the central bank is doing nothing. Okay, and look, how does our system, how does our system changes? Well, you see, not much is happening here. However, enough to get the outcome. Look, because here we're gonna have and look, first thing we should notice is that dg0 is different than 0, so it stays. However, the m0 is equal to 0. Right? So government increases spending while central bank maintains money supply at the constant level. Okay, now we can use again the fact that dg0 is different than 0. We can divide both sides of this equation by dg0. So we get 1 here. Here we change those to partial signs, but here we got divided by dg0. Divided by dg0. And look, all we gotta do now is to use the Cramer's rule to find those derivatives. So again, I'm going to start by calculating Jacobian Jacobian y now, and I'm replacing the first column of the matrix of the determinant of the matrix of the coefficients with vector of exogenous terms. So I got 1, 0, prime, Li, which is equal to Li, which we know is lower than 0. Now, what is the value of our first derivative? We got that that comparative static derivative of income with respect to government spending is equal to y over j over the Jacobian, and it's equal to Li over 1 minus c prime 1 minus t prime Li plus I prime Ly. However, I can simplify those. I can divide numerator and denominator by Li, and I'm going to get that this is 1 over 1 minus c prime 1 minus t prime plus I prime over Li times Ly. Let's do it differently. Ly over Li times I. Okay, what can we say about the sign of it? Well, we definitely know that 1 is positive. We know that this is between 0 and 1. And we know that those two are negative. This is positive, negative and negative gives us plus, positive, positive. We know that this expression is bigger than 0. And look, so it tells us that the higher the government spending, the higher the equilibrium level of income. So what we get here is a fiscal multiplier. Of course, we remember that this expression over here is responsible for crowding out effect. Yeah, but look, I hope you can see similarities between this and what we got for a linear model. The only difference is that now calculations are far, far simpler. Look how fast we got from here to the solution. Because we've got always going to have like ones and zeros, which makes all the calculations very, very pleasant. Okay, but this is the part of the story. We also need to know what is the impact of government spending on equilibrium interest rate. And so we need to calculate another Jacobian. Let's put Jacobian I. So now we replace the second column. And we've got that this is 1 minus C prime y minus T prime Ly 1 is 0. So this in turn is simply negative Ly. Right? Okay. So this is clearly negative because we assume that Ly is positive. So this means that partial derivative of interest rate, equilibrium interest rate, with respect to government spending, which is equal to Ji over J, is equal to negative Ly over 1 minus C prime, 1 minus T prime, Li plus Ly plus times I prime. Now, we've already calculated that this is lower than 0. We know that this is positive, but it has minus. Minus and minus is plus. We know that this expression is positive as well. So what do we learn from that? Look, we learn that regardless of what is the general form of the IS curve, within this model, increase in government spending is associated with the higher equilibrium level of income and higher equilibrium level of interest rate. And look, this actually connects all the channels that we had before. We've taken into consideration all the nonlinearities and relationships between these variables that we assumed at the beginning. But look, this is still the same story that we've told before. Higher government spending means higher aggregated expenditures. Higher aggregated expenditures mean higher GDP. However, higher GDP means higher money demand. Higher money demand, having the same money supply, and remember we assume that money supply is not changing, means higher interest rate, right? And we remember that this actually continues. Higher interest rate means lower investment means lower aggregated expenditures, and lower GDP. And I hope you remember that this part that starts from here, this is what we call crowding out effect. Okay, so look, now that you see how easy was it for us to get to describe fiscal expansion, let's do now monetary expansion. Okay, so what do we need to change here? We're going to start, well, here we need to change monetary, fiscal to monetary. And now, before we were assuming that government spending stays at the same level while money supply is changing while money supply stays at the same level. Now we're assuming the opposite. So what would happen if central bank increases money supply while government keeps the level of spending at the same level? Look, our system changes into 0, dm 0, right? Now, if we divide both sides by dm0, that is different than 0, we get 1 here, and dm0 here, dm0 here. So again, quite easily, we can calculate comparative static derivatives. Okay, and then we start with Jacobian J, y, and it is equal to, we replace the first column 0, 1, negative I prime Li, which is equal to I prime. Alright? I prime tells us what happens to investment when interest rate goes up. We know it's negative. So, first comparative static derivative that we wanted to calculate here, so impact of monetary expansion on income, which is given by jy over j, is equal to I prime, okay, over the Jacobian. And we know that the Jacobian is negative. Wait, let's write. Need to finish proper. 1 minus c prime 1 minus t prime li plus I prime ly. Now, we know that the Jacobian is negative. We know that this expression is also negative. So negative divided by negative gives us positive. And we see again that when monetary authorities are increasing money supply, so we've got money expansion, this increases the level of GDP. Okay, now let's move to interest rates. Okay, we're going to draw a new graph. Okay, so what is happening now? So we calculate Ji, and Ji, we replace the second column as 1 minus c prime, 1 minus t prime, y, 0, 1, and this is equal to 1 minus c prime, 1 minus t prime, which we know is somewhere between 0 and 1. Now, comparative static derivative of equilibrium interest rate with respect to money supply, which is given by Ji over j, is equal to 1 minus c prime, 1 minus t prime over 1 minus c prime, 1 minus t prime li plus I prime ly. Okay, now again we remember that Jacobian is negative. However, this expression over here is somewhere between 0 and 1. And if it is between 0 and 1, it's positive. So we know that this must be negative. And again, we've got the same result. Increase in money supply decreases equilibrium interest rate. Finally, we can put this on the graph. So we got some IS, some LM, and we start with given equilibrium level of income and interest rate. However, as central bank increases money supply, LM moves to the right, and now we've got higher equilibrium level of income and lower equilibrium interest rate. Okay, so I know that the setup here is a little bit terrifying. However, I hope you can see that the calculation of the model is way easier, right? Especially in terms of this determinant, you basically finish in one line. This is due to the fact that now we've got just our exogenous terms are just 0 and 1, which makes calculation simple. And look, those results are far more general than the ones that we had when we were using just linear function, because we were assuming there that functions are actually linear. Now, this is no longer the case. Those can be functions in any form as long as their principal assumptions about their partial derivatives are fulfilled. Okay, and look, In the next video, we're going to apply implicit function rule to ISLM-BP model. Remember, last time we were doing it in a linear way. However, when you do it in a linear way, first, the model is less general, and we actually haven't finished it. We just calculated equilibrium for income and interest rate because I knew that calculating equilibrium exchange rate is really time-consuming, and actually it wouldn't tell us much about the new information coming from the model. Now we will see different story. We will be able to calculate comparative static derivatives of all three variables, so income, interest rate, and exchange rate. We will be able to get very clear results, and they will be very, very easy to obtain. Okay, for now this is it. Thank you for your attention, and see you in the next video.